The thing I want to discuss today is the fact that if you're interested in the learning sample complexity instead of the Glivenko-Cantelli sample complexity, you can get a much better bound. So remember that the original question we started with a long time ago was to estimate the probability there exists some function in your class with the following property. Its empirical averages are small, but its actual averages are large. And we wanted to estimate this probability to show that this probability is less than some delta if n is large enough under the, and get an estimate on how large n should be for every epsilon and delta. Now, what I did so far was to estimate the probability that the supremum of f in f of e mu f minus e mu n f is greater or equal than epsilon. So that's what we did up until now. Now, I want to explain the main difference between this and this. Clearly we have this inequality, right? This is always less than this, but there's something deeper involved. The point is that here we want to ensure that empirical averages in some sense represent the actual averages for every element in your class. Okay? That's what it says here, that the worst deviation you can get from the empirical averages to the actual averages going all over your class members is sufficiently small. This means that this probability is small. Okay? But in fact, we don't care in a learning scenario, we don't care about that. We're only interested in functions which are almost empirical minimizers of the loss. Remember, our learning algorithm produces a function which is an almost minimizer of the loss. So for our kind of function, this would happen. And what we want to show that for functions which are almost minimizers, the empirical average and the actual average should be close. So here, this should hold for every function in your class, and here, this should hold only, in a sense, for functions which are eligible to be empirical minimizers. Now, the problem is, and that's the main difficulty in analyzing this kind of a condition, is that the function you produce is random, is sample dependent. So, in some sense, you can't say, I'm fixing a class, a subset, so let's assume that this is your original f, okay? You can't say, I'm fixing a subset of f, and I want to check a Glivenko-Cantelli kind of condition for that set. Because the functions you're interested in are random. They're produced as empirical minimizers. They're sample dependent. So for every sample, you get a different set. A different set of almost minimizers with respect to that sample. And at first, you don't know. This set might jump around all over F. In some sense, if you go over most of the samples, there's the possibility that you cover the entire F, in which case you go back to this condition. So, although in some sense one would expect to get a much better estimate here, it's not clear how to get it. Okay? That's the first point I want to make. The second point I want to make has nothing to do at first with this connection. It has something to do with, let's call it, the importance of let's call it additional knowledge. Let's return to this. You remember I wrote on Wednesday Talleyrand's inequality in Massad's version, and which was simply a concentration inequality. Now, the point is, and that's sort of a general principle, that if you have some knowledge on higher moments of the random variable, you can get a better deviation estimate. So, for example, if I give you a Gaussian random variable, I will just give you information about its expectation. You can't tell me anything about the way it behaves because it really depends on the variance. If you have a very large variance, you have a problem. The same thing goes in general for random variables. If you just know their expectation, it usually isn't enough to give you an estimate on the rate, or good estimate on the rate of decay. You can say something, but it's usually not strong enough. And the more information you get, the better estimate you'll get. So, for example, if you know something on the variance or on other moments of the random variable, you'll probably be able to get a better deviation estimate. And the way it shows in Massat's result is, remember we had the random variable z, and Massat's result said that z is bounded by the expectation of z plus an error, and the error was something of the order an absolute constant times sigma square root of x plus bx. This is the L infinity estimate over your class. This is the worst variance. And you can get similar result if you replace the variance with other moments which are, bigger than the first. But traditionally people like to work with the variance. So I'm going to do stuff with the variance. That gives you sort of an indication that if I can tell you that the class you're interested in consists of function with small variance, you'll get a much better deviation estimate here than you would get in general without knowing that elements in your class have a small variance. So if I can, in some sense, take my class, right, and in our case, the class in some sense is centered near zero, right, because the class of functions we're interested in was of the form g minus t squared minus pgt minus t squared. So in some sense, 0 is the element you're shooting for. You don't know where it is, but that's the element you're shooting for. So suppose I was able to show you that in fact you're not interested in the entire f. You're interested in a sufficiently small ball near 0. You can take this condition and transform it to this kind of a condition, but not over the entire class, but over a really small subset of the class. Then you can get a much better estimate because you'll have an additional information that you're only interested in a random variable with a certain control on its variance. And that's the philosophy. The philosophy was to reduce this case to this case with an additional information. So how do you do that? That's what I'm going to show you now. The idea is very simple. The idea is to take your class and divide it into two subsets. One is a subset which has functions with a large variance, and the other is a subset which has small variance. Right? So in some sense, if this is 0, I'm taking this class and looking at this and its complement. And the probability that you'll have a function which does that is exactly the sum of the probabilities, or bounded by the sum of the probabilities. So you know there's a probability that there exists a function f such that this is bounded by epsilon, but this is larger than 2 epsilon, is bounded by the probability that there exists an f in f such that this holds both these conditions and E mu f squared is less than epsilon plus is greater or equal than epsilon. Okay? I haven't done anything clever so far. Okay? All I did was split the classes into two subclasses in a sense. Okay? Now, let's look at these. This is exactly what I want. Okay? I have the probability that you have a large actual expectation, a small empirical expectation, but you're looking at a class with at functions with a small variance. So if this is large, this is small, then the difference has to be large. So let's call this 1 and 2. So this is 1, this is 2. So 1 is trivially bounded by the probability supremum of f in f, but not on the entire f, only functions with small variance at E mu f minus E mu n f greater or equal than epsilon. Okay? So this is exactly a Glivenko-Cantelli kind of a condition, but now you've restricted your class to elements of small variance. And that's fine, but that's easy, right? That wasn't the problem. The problem is how to control this set, this probability. And in general, you can't do it. Right? In general, there is no hope to ensure that for every class of functions, this thing would hold. You need to impose another assumption on your class for this to work. And the assumption you impose is the following. So assume that there is a constant B such that for every f in f, the variance of f is bounded by the expectation times b. So in some sense, you can control the variance of every element of your class by its expectation. So saying you have a small expectation means that you must have a small variance in this case. Usually it's not true. Now I'm going to put this assumption in a box because this is a very important thing. And in order for my analysis to work, or to be justified in the learning theory sense, I'll have to show you that for every interesting class, yes, this holds with a decent constant. Okay? Let me give you just one example of a class of functions for which this holds. Suppose that you're interested in what's called proper learning. Proper learning means that the target concept belongs to your class. Okay? So if your target concept belongs to your class, put this over here. So, for example, if G is your class, and T belongs to G, how does the loss class look like? So the loss class is of the form G minus T squared minus P pgt minus t squared, where g is in g. But if you know the t is in g, what's the nearest element to t in your class? You can take t itself. So this has to be t. So this is 0. So your loss class is simply g minus t squared, where g is in g. Okay? Now the good thing about these functions is that they're non-negative. Okay? So take any function of this form and you want to show that the expectation of the loss function squared is bounded by some constant times the expectation of the loss function. So we have the expectation of g minus t squared times, well, it should be to the power 4, right? Bounded, let's write it like that. This is the function, and this is how you compute its variance. Bounded by b, the expectation of g minus t squared. Okay? Now this is true because your functions are uniformly bounded. Okay? Write this as e mu g minus t squared times g minus t squared. Okay? This thing is bounded depending on the ranges you select in advance for your class members and your targets. So now assume that your class is just functions into 0, 1, the interval 0, 1. So this is into 0, 1, this is into 0, 1, the difference is into minus 1, 1. You square it, you get something which is in 0, 1, this is less or equal than 1. And now you have something which is less or equal to 1 multiplied by something positive. It's bounded by, and you can take b equal 1. Okay? So the constant here will only depend on the ranges you take for your targets and your original class. In this case, which is easy. It's much more difficult, but still true, that even if t doesn't belong to your class, okay, here I had the assumption that t belongs to g. Even if t doesn't belong to your class, you can still prove something of this form. Well, what's written up there. And this is a nice geometric argument which is based on the properties of the nearest point map onto convex sets. So the only case, let me be absolutely accurate. In general, what you can show, and I'll write it, in general, if G is convex, and F is the loss class associated with G, and T is not necessarily a member of G, okay? T may not be in G. Okay? Then, for every f in F, E mu F squared is bounded by 16 E mu F. You can show that. The reason that this holds is because of the fact that you can, in the case of a convex function, in some sense, you can identify or characterize the nearest point to T. So in Hilbert spaces, there's a nice argument that if you want to find the nearest nearest element to T in a convex set, you can identify it using inner products in some sense. I'm not going to get into that at all, but it's a really standard argument. It's something about computing this angle. Okay. Another interesting thing I'm not going to mention at all is that it's true even instead of the squared loss class that we took here, you take a different kind of loss class, an LP sort of loss class, but then the proof is much more complicated. It has you have to use properties of the LP norm, and that's far beyond the scope of what I want to say here. So, yes, not exactly. No, you can't have, it's not exactly the characterization. It has something to do, I'm going to say something, I won't regret I said it, but I'm going to say it anyway. The interesting property of the nearest point is the fact that if you take T and you take this distance and you take this ball, right, the ball which is exactly intersects the set in the nearest element, and then you take the hyperplane supporting this ball at this point, it separates the two sets. The ball is on one side, your convex set is on the other. If you use this in L2, that's all you need to get this angle characterization. That's the property that gives you the angle characterization. So in some sense, yes, that's exactly the same property. That's exactly the same property you're using in the LP spaces. But it's hardly as straightforward there. You need quantitative estimates on the way a ball behaves, on the geometry of the ball. How much does a ball look like a ball? Okay? But the proof is really nice. I like it. But I'm not going to talk about that here. But as far as I'm concerned, it means, what I've said here means that I can make this assumption, right? Because in all the interesting classes, or all the classes I'm interested in, squared loss classes constructed by functions with a uniformly bounded range and a uniformly bounded target, I can make this assumption and I can compute it in advance, right? You give me some knowledge on the norm, on the infinity norm, the bound you have on the functions, I can tell you what B is. And B isn't too bad, right? It's 16 here. So I'm going to make that assumption. And now I'm going to use this assumption to estimate this probability. Okay? So let's go back to what we want. We want to estimate, we had no problems in estimating the case where you take the elements in your class which have a small variance. Now I want to show you how to handle elements which have a large variance. So I want to estimate the probability that there exists a function in F with the following property. Mu and F less than epsilon. Mu F is greater or equal than 2 epsilon and a large variance. Let's just make sure that this is the right scaling. Okay. Like this. Okay, now I want to get in a similar way to the deviation estimate, I want to go to a Glivenko-Cantelli type of estimate like I did up there. I can't do this, right? Because if I do this, what I'll get is the supremum over all elements in your class with large variance, and that's exactly what I want to avoid. So I need to do something a little smarter. So what I'm going to use is this. The fact that I have, in some sense, a large expectation. So I know that this expectation is larger than 2 epsilon. Okay? That's what I want to say. Right. So I'm going to write it in the following way. I'm going to write it as, well, it's not going to be very clever. I'm going to write it as, I want to say, right, well, okay. I know this. So I'm going to write in UF and sort of decompose it into 2 parts in a very stupid way. Okay? Nothing smart. But now I'm going to use the fact that this is greater than 2 epsilon. So this is greater than epsilon. Okay? And we know something else about epsilon. We know that epsilon bounds this. So this is greater or equal than half in UF plus in UNF. Okay? Nothing smart so far. Oops. Okay, just writing what I have. I have in UF greater or equal than half in UF plus in UNF. Okay? So, as long as I'm here, if I'm here, then this holds. Okay? But this means just moving this to the other side and remembering the fact that under my assumption this is small and this is large, that this implies that the absolute value of in UF minus in UNF is greater or equal than half in UF. Okay? So this isn't a Glivenko-Cantelli type estimate yet, right? But it's getting there. Right? We're measuring the difference between actual means and empirical means, but the way we measure the differences is not according to a fixed scale epsilon, but according to a scale which depends on the function we're looking at. Okay? So it's not there yet, but it's a step, maybe a step in the right direction. Right? So let me just write this way. So this shows you that the probability that there exists a function with the following property: in UNF less than epsilon, in UF greater than 2 epsilon, and EF squared greater than epsilon is less or equal than the probability that there exists an F in F. Now, I'm not sure yet which of these properties I'm going to need, right? So I can assume all of them for the sake of argument. But here I have another additional implication that this happens, right? I haven't done anything. Now, I want to make this look like a Glivenko-Cantelli kind of a condition. To do that, I'm going to do 2 things. I'm going to, in some sense, multiply everything by epsilon here and divide everything by this. Okay, this is, in some sense, a scaling idea of the class. I'm looking at elements I started with this. I know how to handle this. This is the elements with small variance. Now I'm here. Now what I'm going to do is to scale elements here and in some sense put them in this ball. Okay, that's the idea of this of the scaling. And the reason I can divide by this is because I know that elements here are large. I'm far away from 0. I can divide this. It's not a problem. So what I'm going to do is define, okay, not yet. What happens if I multiply here by epsilon and divide by E mu f? This condition is equivalent to having E mu of epsilon f. Right, this is the factor I'm multiplying things by, minus E mu n greater or equal, and here I have half epsilon. So this condition is equivalent to this condition. This is the GC condition. Right? This is first of all, everything here is well defined. I didn't divide by something which is 0. Right? So everything is well defined. But this is a GC condition for the new class of functions. And the new class of functions is defined in this way. So let H be the following. It's all of the functions epsilon f divided by E mu of f, where f is an f. And you know two things about it. Now I can select from here which data I need. So I'm going to use this, and I'm going to use this. Okay? So E mu f greater than 2 epsilon E mu f squared greater or equal to. Okay. Now let's see which elements. What's the properties of these of this class of functions? If I'll be able to show you that every element in this class of function necessarily has a small variance, I'm done. I've reduced the problem to a Bivenko-Gantelli type of a condition for a new class of functions. It's not clear yet on how does this function relate to f. I just want to change something here. I'm going to do 2 epsilon, and here epsilon. Okay? So here you have 2 epsilon. There's a reason behind this. Okay? So I'm going to show you that all the elements here have a small variance. That will mean necessarily that I've reduced the problem to a GC type of condition for a new class of functions with small variance. But then there'll be an interesting question on how does this new function relate to my original one. Okay? And I'm going to show you that also. But that's the idea. Okay? So all I needed to show you are 2 things. Right? Remember Massat's inequality. There were 2 important parameters which governed everything, or actually 3. One is the uniform bound on the functions. I have to show you that these functions are uniformly bounded. Okay? The second thing I have to show you is that they have a very nice variance, that the variance is small. Okay? And how small? Well, here I'm interested at the deviation at scale epsilon. I want to show you, I have to show you that the variance is of the order proportional to epsilon, where the proportion is some absolute constant. That's the second thing I'll have to do to convince you that it works. The third thing is, if you remember correctly, the third term in mass sets inequality, or actually the first term, was the Rademacher complexities associated with the class we were interested in. Then you will have the Rademacher complexities of this thing. I have to address the problem of how to estimate this. Right? Assuming that everything goes well. Okay? So that's what I'm going to do. I'm going to show you that the first two are easy, and then I identify this class and show you why the third one is also easy.
Question?
Yes?
Why absolute value is necessary?
It isn't. It isn't. I just wanted, if this is true, then this is true. Right? Because this is positive. Okay? The reason you're right, I don't need that. I can have the one-sided inequality, but it doesn't change much. Because from the deviation point of view, the way to get the two-sided inequalities is to get the one-sided inequalities twice. So it's the same estimate, essentially. Okay. Well, I'm still to use this. I haven't done anything with this assumption. I'm going to erase it, but remember that it's there. So, I need to show you, to start with two things. One, is our elements in H uniformly bounded? Okay? So, take any element in H. How do you get an element in H from an element in F? You multiply by something. This is absolutely bounded. This is bounded by 1. That's our assumption. But by what factor do you multiply things? That's where this comes into the game. Okay? Since you know the expectation is greater than 2 epsilon, you're multiplying f by some factor which is smaller than 1. It depends on f, but it's some number between 0 and 1. If you multiply things with some number between 0 and 1, you just reduce things. Okay? So, H, let's write it like that. Every H in H is of the form alpha times f. I'm writing alpha sub f just to remember that this constant isn't an absolute one. It depends on the specific function you're looking at. But you know that alpha f is between 0 and 1. Therefore, the infinity norm of h is less or equal than 1. In general, the infinity norm of h is less or equal than the infinity norm of f. That's one thing. The second thing is I want to estimate the variance of elements in H. Okay? So how do you compute the variance? So I have to take the expectation of H squared. Okay, so let's see what we have here. That's the expectation with respect to mu of 2 epsilon f over e mu f squared. I'm taking all the constants outside. So that's 4 epsilon squared divided by e mu f squared multiplied by ef squared. Okay? That's just computing the variance, nothing smart here. Now, I need to use this assumption. Here, I have the variance of f, and here I have the expectation of f squared. But I know that the variance of every element in f is bounded by a constant times the expectation of f. So this is less or equal than 4 epsilon squared times b times EF divided by EF squared. Okay? This and this cancel each other out. I'm going to write this as 4b epsilon times epsilon divided by EF. Oh, let's do it like that. 2b epsilon. That's the right way to do it. Okay? And remember that the expectation of f is greater than 2 epsilon on this class. So again, using the same argument as above, this is a number smaller than 1. So this is less or equal than 2b epsilon. So what we get is a GC type of condition at scale epsilon over a class of uniformly bounded functions, and the variance of every one of the class members is proportional to the required deviation. And that's exactly what we were shooting for. And this is a number. It depends on the property of the class, right? So in a convex loss class, this would be 32. So to conclude this whole thing, or almost to conclude it, so the probability that there exists a function in f with small expectation, but small period of expectation, but large actual expectation, is bounded by the probability that supremum of f in f with the property that in u f squared, the variance is less than epsilon, in u f minus in u n f, greater or equal than epsilon, plus the probability that supremum over h in h, and I'm going to call it h epsilon, okay? For h epsilon, write it in a minute, in u h minus in u n h greater or equal than epsilon, where h epsilon is all of the functions epsilon f divided by in u f, in u f is greater than 2 epsilon, in u f squared greater than epsilon. And I've shown you that this class of functions consists only of functions for which the variance is of the order epsilon. So forget where that came from, and just remember that fact. So you have a fixed class of functions, right? You fix epsilon, you have a fixed class of functions, and you know that its variance of the worst member is proportional to epsilon. Now before I'm going to continue, I'm going to do one more step. I want to identify this. So now for that, I'm going to do something which seems at first like losing a lot, but in fact I'm going to convince you that you're almost losing nothing. And that's, in some sense, the right thing to do. Let's assume that this is sort of a schematic version of our class F. Just these points. This is 0. Now, all I know is that every element here is, you take f and you scale it by some proportion where that proportion depends on f. So in fact, your real picture of h could be something like this, right? It's maybe a point here, maybe a point here, maybe a point here, maybe a point here, and here. All these points have one property in common. They're on the line connecting the original number of f with 0. Right? Because you get them by multiplying f by a number between 0 and 1, so they have to be in the same direction as f. And since you multiply between 0 and 1, they're here. So what I'm going to do, I have no way of figuring out exactly where I am here, so I'm just going to take the entire lines. Okay? So now I know that h epsilon is a subset of this. Okay? Regardless of this choice of epsilon, regardless of anything. For every epsilon, h epsilon is a subset of this set, let's call it A. But another thing happens. F is also a subset of this, right? I started with F is equivalent of no scaling at all. So F is also a subset of A. All right? So what I know is now you take your class F, you connect its elements to 0. You look at the union of these intervals in a sense. All right? Now, this first term would be bounded by taking all the elements in A, okay, with the additional assumption that they have a small variance. But the same holds for this. This is exactly as bounded by taking all the elements in A, but again we know that all the elements have a small variance. So these two probabilities are bounded by twice the probability that there exists, let's call it again H in A, or not like that, supremum H in A, the expectation of H squared less than, okay, now we have to be careful a bit. Here we had elements, here we had elements with variance smaller than epsilon. Here we had elements with variance smaller than 2b epsilon. I'm going to take the larger of the two. Okay, so I haven't lost a thing. So the variance is 2b epsilon e mu h minus e mu nh greater or equal than epsilon. And as you do the question of finding the probability that an empirical minimizer is bad, to estimating a Glivenko-Cantelli kind of a condition, to a function which is closely related in some sense to f, to the original class, with the property that all of its members have a variance at a scale proportional to the required deviation. Okay? That's the idea. Now, this kind of operation is called star-shaped hull. There's a convex hull, which means taking all the convex combinations. This is called the star-shaped hull. Of F and 0. Okay? And the reason it's called star-shaped is clear from the picture. It just looks like a star. And the formal definition is just take the union of all the intervals connecting elements in your class with 0. I'm almost done, right? I take this, I use Massard's inequality, right? In fact, I had a Glivenko-Cantelli kind of an estimate in general for this kind of situation. And you can show, so the main corollary that you get out of this, or this theorem, let's call it, is that this probability is smaller than delta, just plugging this into Maslow's inequality, okay? Provided that n is greater or equal than two things, an absolute constant times the maximum times the between two things. We had in the usual Glivenko-Cantelli type of a condition. Here you would have the Rademacher average square of the class h epsilon over epsilon squared, and here you'd have b, this kind of a b, log 1 over delta divided by epsilon. Now, two important differences, and that just follows from plugging in Maslow's inequality. I don't want to do that. It's not complicated at all. Two important differences between the usual Glivenko-Cantelli type estimates. In the Glivenko-Cantelli type estimates, here we had epsilon squared. Okay? And the reason we had epsilon squared was the fact that we didn't have any knowledge on the variance of your class. All that we did, if you remembered, was to bound that sigma in the term by something like square root of n, and all we used for that is that the class consists of functions bounded by 1. Here, we know a lot more. We're looking at the Glivenko-Cantelli type condition, but you know that the variance is of the order epsilon. That gives us another epsilon here, which cancels one of the epsilons in the epsilon squared. So that's why we get something like log 1 over delta divided by epsilon. And in a very similar way to what we know in the GC condition, though I haven't shown you, this is the best you can hope for. You can't get, it's possible to show that you can't get a learning sample complexity, this kind of an estimate, which is better than log 1 over delta divided by epsilon. So this is the absolute minimum. So now this tells you that what controls your complexity of the problem is this, your Rademacher averages. But this is the second difference. This isn't the Rademacher averages of the entire class. This is the Rademacher averages of the star-shaped hull, which is larger than your entire class, but now you don't take your entire star-shaped hull, you just take the intersection of the star-shaped hull with a ball of radius approximately square root of epsilon, right? The variance is bounded by a constant times epsilon, so in fact, all that you care about are the Rademacher complexities of this set. Now, in principle, I still have to convince you that this is much better than the Rademacher complexities of the entire set. I haven't said anything about why this is better than taking the entire thing. It's clearly smaller, but maybe if you do something as complicated as taking the Rademacher complexities, it's still too large, and you would still get something of the order of 1 over epsilon squared. I don't know. Right? I have to show you that. I'm going to do that after the break. So let's stop now, take a 5-minute break, and do that after the break.